Hello everyone, I am Firyuza and you are watching Bold Science with Firyuza. In the history of 20th century physics, there is one debate whose significance reaches far beyond science itself. We began discussing it in an earlier video. This wasn't merely a dispute about equations, not merely about quantum mechanics. It was a debate about what it means to understand reality at all. It was the famous confrontation between Albert Einstein and Niels Bohr. They didn't argue about the accuracy of calculation. They argued about meaning. Today we'll examine their position calmly, without myths and oversimplifications. And we'll see that the debate is still not fully resolved. By the beginning of the 20th century, classical physics appeared nearly complete. Newtonian mechanics, Maxwell's electrodynamics, thermodynamics, together they formed a coherent and logically structured picture of the world. Then quantum mechanics emerged. And with it came statements that seemed at first glance almost absurd. A particle may not have a precise position. Measurement affects the outcome. The future is described in terms of probabilities. These ideas were so radical that even the greatest minds of the era found themselves divided. Let's begin with Einstein's position. First, an important clarification. Einstein didn't reject quantum mechanics. He made foundational contributions to it, the explanation of the photoelectric effect, the concept of light quanta, and more. What he rejected was the interpretation that gradually became dominant. Einstein supported a statistical interpretation. At every moment in time, a particle, say an electron, possesses definite physical properties even if they are unknown to us. According to Einstein, an electron always has a specific position and a specific momentum. Our ignorance doesn't imply their absence. So why does uncertainty arise? From Einstein's perspective, the source of uncertainty is not nature itself, but the measurement process. To determine a particle's exact position, we must interact with it. For example, we illuminate it with light. But this interaction cannot be made arbitrarily small because of the finite size of the quantum of action. If we use light with long wavelengths, the particle is only weakly disturbed, but its position is determined imprecisely. If we use light with a short wavelengths, the position is measured more precisely. But the photon carries higher energy and transfers an unpredictable momentum. As we refine the position measurement, we lose information about momentum. The key point is this: the particle had both a position and a momentum before the measurement. We simply destroyed that information through our intervention. That is Einstein's point of view. The product of the change in position and the change in momentum equals the action we perform on the particle, and this action cannot be smaller than one quantum of action, that is Planck's constant. This is a fundamental limit. It is precisely this that makes the measurement inherently imprecise. But it is important. This is a limitation on our knowledge, not on reality itself. Einstein also believed that the wave function doesn't describe the real state of the particle, but merely allows us to calculate the probability of finding the particle in one place or another in space. According to Einstein, the wave function reflects our ignorance. In his understanding, quantum mechanics is applicable as a statistical description of the motion of a large number of particles, but doesn't provide a complete description of one specific particle. Hence the famous remark, God doesn't play dice. From Einstein's position, two logically possible conclusions can be drawn. One possible conclusion is this: the uncertainty principle represents a fundamental limit to what we can know. In that sense, the microscopic world would be inherently unknowable in full detail. Einstein rejected this conclusion. He didn't accept that nature itself places an ultimate barrier on understanding. A second conclusion was much closer to Einstein's thinking. He believed that world is intelligible. Therefore, he was convinced that quantum mechanics is a provisional and incomplete theory. At some deeper level, a more fundamental framework should exist, one that preserves the successful predictions of quantum mechanics, but allows a precise description of a particle's trajectory. Now let's turn to Bohr's position. It was far more radical. Bohr wasn't simply saying that we lack information. He argued that certain properties don't exist prior to measurement. From Bohr's perspective, at any given moment, a quantum object doesn't possess a definite position, doesn't possess a definite momentum. It is, in a sense, spread out both in ordinary space and in momentum space. The wave function provides a complete and exhaustible description of this spread. In that sense, it describes reality itself. Bohr's key idea was the fundamental role of measuring apparatus. Measurement is not passive observation. It is a physical interaction between a quantum system and a classical device. The outcome of a measurement doesn't reveal a pre-existing property. It brings that property into being. This is a profound shift in how we think about reality. Bohr introduced the principle of complementarity. What does it mean? Certain properties of quantum systems contradict each other, yet are both necessary for a complete description. For example, position and momentum, wave and particle. We can observe one or the other, but not both at the same time. To illustrate this, let's consider a classic thought experiment using diagrams that Bohr himself drew. If a particle passes through a narrow slit, its position is well defined, but its interaction with the edges of the slit introduces uncertainty in its momentum. If we make the screen movable and measure its recoil after a particle passes through it, then we can determine the particle's momentum more precisely. But the particle's position becomes correspondingly more uncertain. And this is not a technical limitation. It is a fundamental one. Bohr believed that every quantum object is both particle and wave. In other words, a quantum system unites two mutually exclusive properties. It is precisely the presence of two mutually exclusive properties in a quantum object that doesn't allow us to visualize it. Bohr emphasized that no experimental arrangement allows us to observe both the wave and particle aspects of a quantum object at the same time. The apparent contradiction never shows up within a single experiment. Physics, in his view, speaks only about what can be measured. In Bohr's interpretation, the uncertainty relations formulated by Werner Heisenberg don't reflect our ignorance as they express real features of the quantum world. Nature itself is structured this way. This approach became known as the Copenhagen interpretation, developed primarily by Bohr and Heisenberg. It stands in sharp contrast to classical thinking. The Copenhagen interpretation abandons definite trajectories, visualizable pictures of quantum processes, and objective description independent of measurement. What remains is the mathematical formalism, predictive power, measurement outcomes. That is why quantum mechanics can seem almost absurd at first encounter. If we reduce the debate between Albert Einstein and Niels Bohr to a single question, it becomes this: does physical reality exist independently of measurement? Einstein answered yes. Bohr replied that the question itself is misguided. Experimentally, quantum mechanics has been confirmed with extraordinary precision. It underlies modern engineering calculations and countless technologies. Yet its interpretation remains open. Modern experiments have proven Einstein and his supporters wrong, but they haven't eliminated the philosophical question. What exactly does the wave function describe? The world itself or our knowledge of the world? This debate matters far beyond physics. It touches on the nature of reality, the role of the observer, the limits of human understanding. And perhaps Einstein was right when he said that the most incomprehensible thing in our world is its comprehensibility. And the debate between Einstein and Bohr may not be a mistake of the past, but a starting point for the future of physics. You've been watching Bold Science with Firyuza. Subscribe, like the video, and see you in our next video.